Area moments of inertia. By the end of this section, you should be able to explain what an area moment of inertia is, and we're going to be calculating the area moment of inertia of composite shapes about their own vertical and horizontal centroidal axes, and we're going to be using only the tabular method for this course. So first, we want to know what is the area moment of inertia. Well, one way we can think about what the area moment of inertia property or measurement is it's going to be a cross-section's resistance to bending about an axis. So what does that mean? How can we think about that? Well, back to that opening picture, if we imagine having a yardstick and we have a very tiny person walking across it, there's two basic ways that we could orient this yardstick. We could have the larger dimension up and down, the vertical dimension, or we could rotate it 90 degrees and have the larger dimension of the yardstick be the horizontal dimension. And we can think about how easy or difficult is it to bend the yardstick in these two orientations. So with the vertical dimension being the larger dimension, we can see, as illustrated here, less bending. It's more resistant to bending when we are applying this vertical load on the dimension that is the larger dimension. However, when we rotate it 90 degrees and use that orientation and now apply that same vertical force, we see that there's more bending. It's easier to bend when it is oriented 90 degrees counterclockwise or clockwise from the other orientation. So what's the difference here? Again, the larger dimension is along the same axis that we're applying the load in the left picture, but in the right picture, the shorter dimension is parallel to the direction that we're applying that same load. So we can think of it as the resistance to bending, at least for the same material, for the same loading. One direction might be harder to bend than the other. So the larger the area moment of inertia, we can think of that as a higher resistance to bending around a particular axis. And we can see, as illustrated here, the area moment of inertia calculation is going to be dependent on the orientation of the cross-section, and we'll get to that in a bit. This measurement is a geometric property, and it doesn't matter in this picture, is it made of wood or metal, is it made of a ceramic? The area moment of inertia is going to be the same calculation independent of material. That is, if it is a homogeneous cross-section made of only one material. In more advanced classes, you may look at cross-sections made up of more than one material, in which case the moment of inertia calculation will become a little bit more complicated. So we are going to be calculating the moment of inertia about what we call the centroidal or the neutral axes. The centroidal or the neutral axis is going to mean the same thing. They are the axes that pass through the centroid of our cross-section. And we're going to have a horizontal one and a vertical one. So the calculation is going to be dependent on the shape of the cross-section. So here we list the two basic shapes we're going to see, rectangles and triangles, but we're going to be looking at composite shapes as well, and it's going to have a similar type of solution strategy as we saw for calculating the centroid of a composite shape. So we see here for a rectangle, we're going to be computing the moment of inertia using generically BH cubed over 12. Now, if you look in different books, B is going to be the base, H is the height, that's why they're called that. But really how we want to think about this is that we are cubing one dimension and the other dimension is linear. Always think about H, or the cube dimension, as being the dimension that is perpendicular to the bending axis. And B, the linear one, as being the dimension parallel to the bending axis. So going back up here to these two pictures, in the left picture, we are cubing the vertical axis because it is bending. We would say it's bending around the horizontal axis here. So in the left picture, the larger dimension is being cubed and the smaller dimension is only to the first power. When we go into the right picture, we are still bending it around the x-axis, we would say, or the horizontal axis, but now The cube dimension is much smaller than the dimension that is horizontal, the linear dimension. So that's why the left picture is going to have a larger area moment of inertia calculation than the right. Because it depends on the orientation, it depends about which or around which axis we are doing the bending. Now, there's other cross sections that we can calculate, and we'll see some on the forthcoming slides. But if we have a very strange cross-sectional shape, we might be able to look it up and compute it, or we're going to be able to turn it into a composite shape made up of several rectangles, triangles, circles, etc. As we saw with the centroidal problems, we can, when we're computing our moment of inertia, we can cut out shapes, in which case we're going to apply a negative value to the moment of inertia. However, any physical shape, its composite or its total moment of inertia must be positive. Cutout shapes within it that we use to build it up can be negative, but in total, it must have a positive value. Now, typically, we are only going to compute the moment of inertia about horizontal and vertical axes. However, we can find the moment of inertia about any oblique axis as well. So any axis that is not purely horizontal or purely vertical, we can calculate. We will not, though, for this class. We can also look at what we call the polar moment of inertia. Often J or maybe I naught is going to be its notation. And that's a twisting about a longitudinal axis. That's going to come up in the follow-up course, Strength of Materials. It's not going to come up in this course. We're only going to be bending around horizontal or vertical axes in this course, not about the longitude of our section. And I'm going to use for this course the term moment of inertia and area moment of inertia interchangeably. Specifically, the things we're going to be calculating are area moments of inertia. As we're about to see, there are other kinds of moments of inertia. But in this course, the only moment of inertia we're using is the area moment of inertia, so that's why I'll use it for shorthand. We can think about the centroids that we were calculating before as the mean of a cross-section. So on average, where is the area of this cross-section? That's what the centroid was calculating. The moment of inertia, specifically the area moment of inertia, we can think about as the standard deviation of the material. The standard deviation is basically a measurement of, on average, how far apart is our material from the centroidal axis. So when our material is more spread out from the average, from that center, the centroid, we're generally going to have a higher moment of inertia. When the material is on average closer to the centroidal axis, we're going to have a lower moment of inertia. We're going to be using the calculation for area moment of inertia a lot in Strength of Materials, the follow-up to this course, because it's going to come into play when we are calculating different stresses in our material. In a pure statics sense, we're not really going to use this calculation all that much. And in the future, we do want to be careful to not confuse this area moment of inertia with another moment of inertia we use, the mass moment of inertia. In dynamics, we're going to be using the mass moment of inertia much, much more. And the mass moment of inertia is going to be the one that we use with our angular velocities. And we're going to see that the units we come up with here for our area moment of inertia are always going to be length to the fourth power. Whereas a mass moment of inertia is going to be a mass times a length squared. So the quantities are different, they are measuring different things, and we use them in different ways. We're not talking about mass moments of inertia in this course. We use those in dynamics. This area moment of inertia we use in this course, and we'll be using in Strength of Materials.